Alrighty, Heidi, and we are live. I could probably turn the decibels up on this a little bit. Decibel gain. Hello, hello. Oh, it's because the speaker's actually all the way over here. Hello, hello. Yeah, now I got to turn it back down again. Turn this off. Hello, hello. Yeah, I got to set that back down. 15. Hello, hello. All right, cool. Okie dokie. Now to do all the logging ends is pretty sure this needs to be over here further. Yep, I need a light. I need more light. Yeah, I'm going to take this and put it over here. Let's log ourselves on. Ba-da-doo-doo-doo-doo. 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 My channel. Oop, gotta turn the volume down. Let's log ourselves on. There we go. All right. Now I got a nice... Hey, Rupa! Okay. I was saying hi. Ah! That's funny. All right. Now we do the social medias of the... Whoa. What was that? Now we do the social medias of the advertising. So we go on the Facebooks. First we need a link. Hi everybody, how's everybody doing? Let me pick this up a wee bit. There we go. It's probably a little better. View channel, live, share, copy link. Go to the Facebooks. Post. We are live! Yay! Paste. Post. Haste. Post haste. Post haste. Alright. Switch. Update. Share. Are live. Yay. Alrighty. I gotta remember where I left off on this thing. Alright, cool. Cool, very cool, very cool. No, I don't want to do that. I want my wiring diagram. What did I do with that? Alright, we're going to put that up here. And, okie dokie. Now, where are we? Where are we? Alright, everybody, welcome back to the channel. We are going to continue building our zero cross circuit here. It's really not super... Well, I got about halfway through it. We have to install a voltage drop circuit for the signal input. We have to put the capacitor and diode to build out the DC bus. And then the potentiometer, the comparator, then the opto isolator output. Some stuff. Yep, we got some stuff to do. And I'm going to put this right here. Yeah, I think this will... We'll put this right here. All right. As usual, if you are watching this live, then there's only two people on the viewing as it is, and one of them is my wifey, and she is special and amazing, and I love her. And if you're not watching this live, then by all means, Follow along as we do this, and you'll have opportunity to leave comments in the comment section, which I read all of them. So if you ever have any questions, then you post a comment. I'm guaranteed to read it and respond in a timely fashion because I'm a sucker for communication, I guess. Anyways, all right. Let's see where we're at so far. I've got this joint right here. That is the resistor to diode right here. All right. Let me turn this so you guys can see it a little better. There is a bunch of stuff. There is a bunch of stuff. Okay, so I've got our resistor to diode junction right here. Then I have the diode right here. So I should be able to... I don't have a joint here, so I can trim this. Yes. Yeah, so the if anybody's interested, last time we were on, I was having issues with the truck. And since then I've been working on the truck, filled it back up with water. And okay, that takes care of that. Now I still need to build my tag out here, which I can probably do right here and then jump over. Yep, that works. So I put water in the truck, and it seems to be holding. I put the hose back on and clamped it down, and it seems to be holding fine. So that's a good. I did a combustion test on it, combustion leak test, and what that is, that's a test that if there's like a head gasket leaking, then the pressure of the combustion cylinder will push combustion gases into the coolant. That's the idea. That was my thought. Possibly overpressurizing the coolant, which would blow the line off. So the combustion leak test is designed to see if there's any combustion gases being pushed into the coolant. And I tested it multiple times, and it seemed to be fine. So I guess I'm going with that. Right. So the next step is I want to do compression and leak down. Well, compression checks. I have more misfires on cylinders 5 and 6 than I do on all the rest of them. So I kind of want to see what that's about. But assuming that those have compression issues, then I'm going to do a leak down check on those cylinders to see if maybe I have valves not seating correctly or something. It could just be like misadjusted valves because the guy that did the cam didn't exactly do a fantastic job on any of the other stuff. Alright, so I'm checking my resistor values now because I'm pretty sure these are 51,000 ohms resistors. We got green, brown, and red. Green, brown, and red. Yep. 5.1 thousand ohm resistors. Let me put the diagram back. Did I lose it? Right there. Okay. Now I need to put these resistors in here, so that goes here to here. So I'm going to go ahead and stab both of these resistors together. And I'm not sure how they're going to fall yet, but I don't know. We'll see. And then I want to be in this hole. Okay. So I'm thinking, well, I can do it this way. That doesn't really work out that... Does it? It kind of does. What happens if I go here? Nope, too far. You know what? I'm going to straighten them out. I'm going to bend them tighter. All right. Doop. Bend them tighter. Go in that hole, that same hole. Okay. All right, that works. Now I can simply add these to the back side here. Yep, that works. I'm good with that. Okay. Now what we're doing here is we're adding a voltage drop circuit, which is going to split the voltage in half. If I pulled up the circuit in the simulator, I could tell you exactly what voltage that is, but it worked out really well in the simulator, so I'm kind of sticking with that. Setting 320. All right, we got our stuff there. We got our solder here, and we got a little punch. Why is this over here? I don't need this over here. Why is this over here? All right. Oh, see there? It's up to temperature already. I love this thing. Love it. Get a little tip tinning action going on there. And solder this one in. Ta-da! All right. Pretty straightforward. There. Love this soldering iron. It's fucking beautiful. All right, so what we just added is this here voltage drop circuit. So what's happening is we've got this is AC. Well, no, it's not AC. It's DC, but it's pulsing DC. So it's the pulsing DC positive, and then ground. I'm calling it ground. It's a floating ground. So pulsing DC positive and floating ground, and there's 120,000. Yeah, no, 5.1 thousand ohms. So that's 10.2 thousand ohms across here. So 10.2 thousand ohms at, I think this is 11 volts. It's like microwatts. Well, we don't need amperage. We literally just need the voltage. Now so what happens here, right at this point between the two resistors, is it drops to half. So if this is, let's just say it's 11 volts. If this is 11 volts, then this is going to be 5.5 volts right here, right? But it's 5.5 volts at the rectified voltage. So then we can take that signal and reference that back up to the comparator, giving the comparator a usable 5 volt signal reference. And then all we got to do is put the other voltage against it, which again we're going to make adjustable. So we put the other voltage against it, and that's how the comparator uses. So that's the signal that the comparator is going to use to weigh against everything. Now the reason I did this on the back side of the reason I did this on the back side instead of on the front side is space, honestly. So I have the two resistors on the back side, and they come up right there, right? And then I can just jump right over and then bring that line right back up into here. and then figure out how I'm going to tie in the comparator here. Now, I want to tie in the capacitor and the Zener diode over here. That's what I want to do now. Okay, capacitor. That's right here. And just to make doubly sure, that is a, yeah, one millifarads. That's 1,000 microfarads. All right, so that's 1 millifarad. And we have 1,000 microfarads at 16 volts. So this should be the perfect capacitor for this job. Now, got to make sure I orient it correctly because these are biased. You got a negative and a positive. Negative's got to be on the negative. All right, negative bus is on the bottom. So that goes there. And I want to be on what? Probably this run. So something like this. Yep, that works. Okay. Bend the pen over. And then what I'm going to do is I'm going to take this pin over to here. This pin's probably, yeah, I'm probably going to make a bit of a dog leg with this pin. Just to create the, yeah. I like that idea. So I'm going to bring it over here. Bend it like that. There we go. What I'm doing is I'm using the leads of the components to create the traces on the board itself. So I've got this lead going to this over to here for this junction, and then this lead comes up and over, and I'm not using the diode lead because I want the diode lead. I'm going to be taking the diode lead over like this. I might as well bring it over a while. I'm going to be using the diode lead to create the trace going up. And now I need to do the Zener diode. Yep, and the Zener diode is going to sit right on the end. And I need to make sure I get the orientation of the diode correct. So I'm going to take... Oh god, I need better leads for my multimeter. It is a wonderful piece of garbage. Alright, we're going to go over to diode check. Switch to diode setting. Okay. First we're going to try reverse bias. Stay. Nothing. Alright. Then we're going to try forward bias. And 0.69 volts. Okay. That's what I figured. We are... What the hell? My light. Elgato crap is crap. You gotta be kidding me. I need better lights. Oh, God. What the hell? It, like, just died. What the fuck? Alright, yeah, something's going on. Sorry about that. Technical difficulties, because God forbid we... Oh, what the mother-loving... How bad is it without the light? Well, it sucks. This is what I get, though. This is definitely what I get. What the hell? Are you serious? What the fuck? How are you this bad? Don't touch it, I guess? Sorry, guys. Guess I'm gonna have to come up with some better solution for the crappy lights. I'm trying this Elgato light strip up here because the idea seemed like it would be a really good idea. It's a way to get light up underneath here, but I'm really not impressed. So I'm gonna have to come up with something different. Apparently there's a loose connection in there or something, because it just all of a sudden just glitches out and stops. That is not okay. Alright, forgive me. Let's keep moving. Okay, so capacitors in. We were just working on the Zener diode. Confirmed that the Zener diode is good. And I got people dropping like flies, because of course they would. The stream. Oh, I fucking hate technical. You try to get dependable stuff. You try. That's all you can do. Alright. Put that there. Man, that bothers me. That really does, but need to get over it. And then that here. Alright. So we got our Zener diode. That goes here. And here. Yep. Alright, so these traces are a little bit less than straight. That's probably gonna mess with my OCD, but whatever. We'll get over it. Okay, let's go ahead and solder that down. Alright, so we're going to go ahead and solder that down. Now I need to think about how I want to bring... Where's my... I'm about as prepared as a fart in a space. Here it is. I need to think about how I want to bring up the... Oh, man. How I want to bring up the DC bus. How do I want to bring up the DC bus? Do I want to lay my comparator like this? I mean, I'd have to... Do I have to bring it over there? Up the temperature already. Get a little tinny tin action there. And start the soldering. Oh yeah, still don't have a fume extractor, so we're still huffing those nice cancerous soldering fumes. All right, got that. I can trim up the leftovers. So if I bring up, I also want the potentiometer adjustment. Maybe what I should do is, I only need one side, but I need VCC to come here. So VCC to come here. This is where it gets a little more complicated. All right, so I need. I almost wish I would have come off of here with VCC. I can probably still do that. I'm gonna bring this up. So if I need to come in with VCC to the opto isolator, then I need to. Oh yeah, I need to bring up ground. I forgot about ground. I'm gonna have to put a jumper in there, right there. I can do that. That's not too big an issue. All right. So I'm gonna need to bring up ground. Right. So I want my. All right. So I'm gonna bring ground up, and I'm gonna take this over to here, so that I have the VCC bus, and then VCC and ground, and then I can put the potentiometer between them and feed that in. So then I'll have VCC, potentiometer. Right, so ground, potentiometer, VCC, and then I'll just need the signal. All right, I think that works. Bring this over here. And then, you know what? I'm going to use jumpers. It just seems better. And when I say jumpers, I mean these here doodads. So we're going to go on top and add a bit. So at this point, I should be able to get DC 5 volts. So I should be able to get DC 5 volts and ground from that. So that should be my 220 ohms. So I got my diode, rectifier, resistor. So I got my 100 ohm resistor to diode. And that creates that DC side. Right, so now I need to bring the ground up and create a new ground plane. Let's see. Orange. Be a bit shorter. Blue. Just one. Blue. Yep, blue. Okay. So what I'm going to do is I'm going to go to the top side and I'm going to stick blue in there. And then right in there. Alright, that brings my ground plane up. And then, okay. Go ahead and send that over. I don't know what that's going to look like on the other side, but now this one gets a little trickier. So if I put this something like this. First of all, I need to pin out sheet for this. Well, it's going to be ground on one side and VCC on the other. Okay. Can still see you fine. Oh, thank you, babe. I just saw your comment. Guess I wasn't looking in the right direction. Okay. So I have in my list of stuff right here the pinout for this circuit. And what that tells me is I've got VCC right here at the top and ground at the bottom. So I want to flip this over this way. Okay. Oh, for Pete's sakes. Guess I should have saw that coming. All right. Now, if I use this side, oh, this is going to be tricky. Inputs are, all right, so if this is ground, then my input is 2 and 3. And I want this one to come up, and then I'm going to have to bring it up and over. If that's the ground plane, just like that, then this needs to be, right, output A is right here. So this needs to be closer. All right, so that I have an input. Right, so that input is the negative. That's what I want. And then I'm going to have to jump this other input over and do a little skippity-doo-dah for that. And then this goes to ground. And then I need to pull this up to VCC. And that goes over to there. Okay. We have a plan. Indeed we do. All right, now I have a socket somewhere because I want to use a socket. Right, so this is going to be right there. That's fine. And I guess I'll use, yeah, I'll use another jumper over there above so that I can make this one work the way I want it to below. And where's my sockets? Right, because then I'm going to need that VCC bus to, here's a socket. Okay. And the socket, we can use, we can put the socket like right there. Is that how we want it? Right, like that. Come up over here. So I can, so this way I can, oh, you know what? Maybe I can go one shorter with this. And then I can use this for the ground. Do I do ground? I don't think I have a ground for the opto isolator. I think that actually, I think the ground actually goes through the comparator. Okay, so I can do this to ground, so that should be fine, right there. In fact, I can use those traces to do the ground. And then I'm going to take this up to here, this goes to here, this goes to here. So I could probably actually take it even closer, like that. Yes, that works. Now, am I sticking with that? I am. How do I want that? A lot shorter than that. Let's try a yellow. Yep, that's it. Yellow. I'm going to put the yellow right here. Get in your hole. There we go. Okay. Bring that around like that. All right. Now I have that, and then this goes right here, like that. It's 104, right? Yep. In fact, let's see what resistance that is. It should be 100,000, I believe. Pretty fucking close. 90. Well, hopefully it's not a crappy pot. Crappy pot. Okay. Dum-dum. I'm going to go ahead and bring this over this way. Solder to that. And then I'm going to bring this one over this way, because then the other bus will work out that way. All right, so solder here, solder here. Yeah, all right, solder them in place, get it over with. Go back to the wiring diagram. All right. That's almost warm. Now I'm going to be doing some weird stuff with this jumper right here. So that's going to come up. It's going to come over. Right. So I want. Yeah. I'm just going to use a general jumper for that. Is that good enough? Probably. In fact, it could probably be shorter. Right, if I go there. No, I want to be longer than that. Alright, that's warmed up. No comments yet. No dad jokes. Man, that's kind of disappointing. Is what it is. Alright. Go ahead and... Good gun. There. Alright, and then... that one. Okay. Alright, that takes the DC bus, that takes the positive bus, and that anchors our potentiometer in place. Now, if this one's going to be hard, because these are not so bendable. The sockets are a little more difficult. Alright, so if I This needs to be positive over. Do I want to just use a open bus there, and then I can put this one here, right? Like that. Yes. So if I put this one like that, then that will give a place for I don't know why you're being so difficult. Whatever. All right. And this. So this goes right in here like that. Now, how do I need to hold this. Maybe? No. How am I going to hold it? I need a piece of gum. Where's my hot glue gun? I don't know, but I don't want to touch the power either. Okay, maybe if I push this up in the way, then I'll have some tension. Well, that certainly got it somewhere. Okay, so ground bus. Now I need to take that over there. Signals right there. Right, so signals right here. And then the positive, that'll drop down. Because it also, positive also needs to go. Yeah, I can use a resistor for that, I guess. Yes. All right. I'm just going to solder one leg in. I know this isn't super visible, but kind of trying to. There we go. All right. That way, I had to get one of these legs soldered in so it would stay in place. What the hell, man? Why are you being so clumsy? Yeah, that does not look like a solid joint. Why are you being so clumsy? That's better. Okay. Ta-da! You know, everybody, you're free to like drop a comment, say hi. You know, if you want to say hi, if you have a joke, we're all about the dad jokes over here. All right, so this we are continuing to work on. All right, so now I need to take, this is my signal over here to the negative part of the comparator. And then this is, I need to take a signal from here up, over, and then bring it to the positive side, right? That's what I have in here. Yes, I have that run to the positive side. Okay, so far so good. We are moving right along. All right, so what I can do is I can put a jumper on that and solder that in. I can put, I'm going to take this jumper, I'm going to actually put it up here. Give it a little doodad on the end so that we can catch the one side of that potentiometer. Just like that. Right? And then I can take another jumper right here. And that can go right there. Yep. That's going to be a little difficult to do, but that's all right. Maybe what I'll do is I'll give it a little assistance on the one side. If I put it in a hole like that, kind of hold it steady. That'll help. This one's just going to be, well, I could do this. You know what? Yeah, I could do the same thing to this one. I can drop this in a hole right there. Give it a little turn and buggers. Just like that. Drop it in a hole. Drop it in this hole. And oof. There we go. I think that's good. I think therefore I am. Okay, now the trickier one is I'm probably going to have to make this out of something. So, the trickier one here. Oh man, I really need to figure out how to get people to interact. That's what I need to do. Alright, so pinch here to bend there. Maybe bend a little closer. Yep, alright. Good. Pinch here. Bring it up. Okay. And then here to bring it over. Yes, no, maybe so. And trim it to here. And that will create that trace. Just joining. Forgot I was meeting up with my cousin after work. Hey, Tom. How are you doing? Hopefully you had a good time with your cousin. And there are no sorries necessary. But now you got to tell a good dad joke. I wish people would comment more often. Anyways. So Tom, we're just chugging along, making the wiring. So we're following. If this phone would bloody stay on, I guess I need to print these out or something. We're just following our wiring diagram, putting pieces together, not doing anything. Is that how it? Whatever. Gimme. Gimme. There we go. All right. So this trace goes right here. Just like that. Perfect. Give a little downturn. Doing well. Why did the chicken cross the road? Because it had an existential crisis and forgot which side of the road he belonged on? Why did the chicken cross the road, Tom? Alright. Line this up. Oh, come on. Oh, don't be a tool, you fat bastard. Alright, there. Okay, now I have a few jumpers here, and I think I'm going to actually change my mind about putting this through a through hole. So I think I just want this to go to here. All right. And then I need this one more. Ooh, some of that dinner's trying to come back up on me. Hopefully you guys can hear me okay. I'm a little worried it might be too quiet. I'm not sure. Hold on, let me do a... it should be alright. It should be alright. Okay, solder time. I love that soldering iron. Now, I am going to... to get to the dummy, don't ask me. Guy at work who tells the worst dad jokes told this one right... right before I left. But the worst dad jokes are the best dad jokes. Oh, man. That's great. To get to the dummy. Guess I'm a dummy. Oh, man. I have a review of this here soldering iron on the channel. Or do I have a review of this soldering iron? I know I did a review of this soldering iron. I might need to edit it yet. Alright, so this is our split to the positive. Perfect. Anchor that down. Let's get some heat into that. And let's get some heat into that. Alright, and one more. Actually, I need two more. Alright, into that, and then I just need to, on the back side of this, alright, I'm going to straighten this out because I'm OCD. And then on the back side here, I just need to lay this over and make the solder connection there. Man, I really love this soldering iron. Beautiful. Perfect. Knock, knock. Ha! Who's there? Is that Brian? Welcome to the live stream. So who's there? I love jokes. All right. Trim this. Oh, this is coming together. Might even be able to test this thing out today yet. All right, so I guess I'll go back over this again. Sorry, my multimeter is yelling at me. So what we're doing is we're building a zero cross detection circuit. Only this one's a little different than your normal the chicken. See, that's funny. I did not see that coming. The chicken. Love it. So what I'm doing here is we're building a zero cross detection circuit that is adjustable. And the adjustment has to do with triggering the output anywhere on the sine wave that we want it to. And what that allows us to do is that will give us the ability to lead within a certain time parameter, to lead whatever controller we're using. And I guess I really should make a video or something of like why in the first place. And this all has to do with motor controlling on, so phase angle motor control on AC induction motors. So AC induction motors, right? You can't use just a regular switch because you have your sinusoidal pattern. So to properly control an AC induction motor, there's two ways to do it. You can do a VFD, which in most single phase motors is drastically overkill, or you can use what's called phase angle control. Phase angle control allows us to turn on at a specified point in the sine wave, which basically it's kind of the same way, but you're using a 60 hertz duty cycle is essentially what you're doing. But in order for that to work, in order to be able to control the sine wave, we need to know, we need to be able to time it. And that's what this will do. The idea of this is to give a computer a time to let the computer know, all right, boom, we're at 0, now start your countdown kind of thing. That's the whole point of this. And the reason I made an adjustable one is because pretty much all your circuits out there, ooh, I just realized I gotta jump from that output to pretty much all your circuits out there. Everything takes time to operate, right? So all the switches take time to turn on. And even though it's like microseconds, it's still time. When you're dealing with 60 hertz, you only have like 8.25 milliseconds of switch time. So it's an 8.25 millisecond frequency that we're doing on a PWM signal, right? So every millisecond I lose in the amount of time it takes for the controller to see 0, tell the computer that it's 0, and then the computer do its thinking and then actuating of all the other transistors, I found that I was getting up to 2 milliseconds delay by the time it would turn on. And 2 milliseconds out of 8 milliseconds, that's a quarter of the time. So we would never be able to get above 75% duty cycle on the run. Whereas if I can lead the computer by causing the trigger to happen 2 milliseconds ahead of the 0, then I can use my oscilloscope here to pull this in so that it switches dead nuts on 0, making up for all that. So then that gives me 100% duty cycle, which is what I'm looking for. And realistically, if I'm building a circuit, ooh, I just realized I'm starting to run out of space. It should be all right. I can pull this all the way over to here. It should still be all right. When I'm done, like what I can do is when I build my experimental circuit for whatever motor driver it is and whatever controls I'm using and whatever like ICs that I'm actually using, I can use this to fine tune it. And then measure the resistances that I have on here, and then build a dedicated zero cross circuit just for that component. That's what we're doing here. All of this, like, this is the first step in a very big project. The intermediate project, you guys might like this. The intermediate portion of this project involves turning this here coffee hot plate into a Bunsen burner, essentially. I want to be able to. I'm going to make a controller that uses an Arduino and a temperature sensor to use that as like a laboratory heater. And the coffee pot, this is so dumb. So the coffee pot, I'm going to take the handle off and make a bung in there, and I'm going to use this as a boiler. And that is specifically for the point of refining. Right now, it's specifically for the point of refining hydrogen peroxide, but I'll also be able to use it for experiments with vacuum, like to show the pressure temperature relationship in a vacuum of basically any chemical. I can use this. I'll be able to use this to do that, and it should be fairly interesting. All right, so off top, this is just like the first step in the whole thing. Once I have this developed, then I'll build the motor driver. Once I have the driver circuit developed, and then we can install it and build this out, and then we'll do some chemical experiments with high concentrated hydrogen peroxide, which should be exciting. All right. All that, like the big picture here is I want to build a catalyst reaction turbine generator. Yes. I want to use a turbocharger. I'm going to turn a turbocharger and a catalytic converter into a high frequency generator. That's the big picture to the next, which might take, a year or so depending on the progress. Okay, so enough talking, enough chit chat. I need to bring, this is the output. So this is my output that needs to go to the opto-isolator, and this needs to run, I need to power VCC right here, and then I need to bring it over further. I should have used a different, you live and learn. So I'm going to jump here, and then I'm going to power, I need to take a resistor. Oh, I can use the resistor. All right, we're good. So I'm going to put a resistor here to the opto-isolator and power that. I can use the lead from the resistor, wrap around there, tie it back into here. We're good with that. And these pins don't matter, so I'm probably just going to solder one just to anchor it. And okay, so we have the variable DC voltage on the positive, negative, no, negative. I'm a genius. I'm not. I'm an average person. All right. We have ground here. That's good. We have our signal here. That's good. And then we have, so this is our reference. And then this is the adjustable signal that it's comparing it to. And then our output here. So I need to get this output over. I guess I'll jump it over to here somewhere. Yeah. So that goes to the backside of the opto-isolator. All right. This is my opto-isolator. This is my comparator. So opto-isolator. Now I need to pull up the pins of how that looks. Do I have a marking? Yes. You guys aren't going to be able to see this on camera, but there's a little dot that indicates my position of that. So I'm just going to, what I'm going to do is I'm going to pull up I'm going to Google the information of the opto-isolator. So here's something that you have to do when you're working on electrical ICs, integrated circuits. You got to pull up the data sheet for those circuits. So for example, this is, if you look on this, and you can do this, it's actually kind of fun to do. You can do this with any circuit that you see on a circuit board, right? So there's a number written on it. In this case, the number is LM393. So if you look up here, I got the cut sheet for the LM393. And what it does is it gives you the pinout. So it tells you what pins are what. And then it will tell you, like, here's the, oh, you don't get this very often, but here's the actual inner workings of this component. That's interesting. But this is what's really important right here. The ratings. So the ratings are what tells you how this thing works. For example, the power supply voltage, that's VCC. The symbol, right? So power supply voltage symbol is VCC. And then the value. So this can be anything from 18 plus or minus, 36 volts. This can be up to 36 volts. Input differential voltage up to 36 volts. That means one side can be 0 and the other side can be 36 volts. It's the difference between the two. Input common mode voltage range. 0.0, it's actually negative 0.3 to 36. Output voltage, again, is 36. Continuous is 20 milliamps. So about the same as a optoisolator or like a diode. And there's your power dissipation. So if this were like a switch or something, that would matter. But either way, point is, if you're going to be working with ICs, then the cut sheet is what you really want to know. So what I'm going to do is I'm going to look up the cut sheet for our optoisolator here, which is a 4N25. So I'm going to Google 4N25 data sheet. Excuse me. DigiKey is actually pretty good for this. So if I click on DigiKey and disable the fucking cookies, I swear to God. Data sheet right here. Oh, blow me. And there we go. Now I have the data sheet on my 4N25 optoisolator. So if you see right up here in the top, I have the pinout. Very nice. Like I said, there's a dot on the IC that represents the orientation. So I know the top. So right next to the dot is A, which is my diode, and that is the important one. Okay, so now I know how I need to lay this out. And it's kind of backwards. Yeah, so when I put this in here, I need my resistor power to go here, and then this one to go back to signal. All right, so I'm going to be jumping over leads here a little bit, but that is what it is. All right, so I'm going to stick this in here. I kind of would prefer to have a socket for this because it's actually pretty easy to take these things out, but it'll be all right. So I'm going to put this one, when I get it in, right in here. Man, come on. You're just trying to be difficult. I didn't have to use tweezers. This would be a little easier. But it's kind of in a tight spot. Brute force. Ta-da! Alright. And, alright, so that's oriented there. So I need to go in here. Right. Okay, let me get a dab of solder on one of these leads to hold it in place. Have I mentioned how much I like this soldering iron? I don't know if I did in the past, like, 5 minutes. But I do like this soldering iron. Alright, so this lead right here should be useless. So we're just gonna get a blurb of solder on that lead, and then I'm gonna try and lay out everything else. Yes. All right, let's get some. Let me get a little bit of. Let's turn the tip a tiny bit. And I know you can't see this very well. Forgive me. I'm just kind of working with what I got here. There we go. There, that will hold the chip in place while I figure out how to get this. Okay. Now, what I need to do is this pin right here is my positive end. So this is an LED, an opto isolator. What brand is the soldering iron? Oh, this is a TS101. The brand is Miniware. And I really like this thing. It's light. It uses professional grade tips. Actually, you can see this up here. So it uses professional grade tips. It's light. I even have the tip kit. So you can buy a kit. It comes with a bunch. It's only like $100. It's actually very reasonably priced. It comes with a power supply that feeds at 20 volts. But get this, you can either use this power supply, which is plenty, or a USB-C. So check it out. Check this out. USB-C, as it turns out, USB-C puts out 20 volts. Milwaukee inverter. Put the battery in. This works with actually any USB really. But put the inverter in. This gives you a USB-C port. So this lets me run this soldering iron at full power, which I think, don't hold me to this, but I believe it's a 65-watt soldering iron. But this will let me use a Milwaukee battery to power this at full power, 20 volts, just the same as the power supply they give you. And it works great. Or I can do the adapter and feed it the 18 volts. So they also give you a battery cable. They give you everything. It's awesome. So they give you another connector that you can hook up to a battery. So you can just take the M18, forget the inverter, just take it straight battery voltage. Works fine. And the best part is it actually is temperature controlled. Because it uses the professional tips that you would see on professional soldering irons, it's temperature controlled. So when you plug it in, you set your temperature, and that's it. Now, I do need to build a stand. Like I want to build an electrical station, a soldering station, but haven't done that yet. So I do need to build a stand. That's a thing. All right. Back at this. Oh, I'm still getting... Pardon me a second. By the way, Tom, you wanted recommendations on the 5-volt stuff. Excuse me a minute. Got heartburn coming back on me. Wifey boss made me a caffeine-infused banana smoothie. And it's awesome. So, Tom, you wanted some recommendations on the 5-volt system. I've got two things here. That piece and this. I haven't even opened this up yet. This is a 110 to 5-volt power supply. It's pretty much the same stuff that's in your power brick that you plug in, like a USB power brick that you would plug into a wall. If you put this into a box, like a ready box, then you can plug it into 110 and you don't have to worry about the batteries. So this would work. These are very cheap. Literally, I just got them off of Amazon, and there's like 5 of them, and I think it was like 20 bucks. But that gives you a reliable, I believe it's 300 milliamp supply, which should be fine for doing the power to your transducers. And the other way is, you might remember that thing that Sergeant Coombs posted on that one post. Oh, try the LM8, whatever it was, 7805. That is what this is. So the LM7805 is what's called a power regulator, or a voltage regulator. It takes up to 36 volts. Yep, 7805. Let me put this right in the middle here. Bloop. So this chip right here, this chip will take up to 36 volts and produce a stable 5-volt power up to 1 amp. I actually got this kit off of Amazon that came with all the, they do recommend capacitors on either side that are stabilizing capacitors. Here's the difference. With this chip, it's kind of like a resistance-based chip. Maybe MOSFET base? Is MOSFET the variable resistance gate? Either way, this produces heat. But what this would let you do is you could tie a 9-volt battery. You have to be 1.2 volts over 5 volts. So your minimum input voltage needs to be like 6.2. So if you took just one 9-volt battery, you could probably put a couple in parallel for better amperage, but or, you know, longer lasting. But if you took a 9-volt battery, you could use this to drop the 9 volts to a stable 5 volts and use that to power your transducer and then read the milliamp coming off the transducer, which most transducers are milliamps. So that needs, you know, you need to register the amperage. So you're going to, you know, tie the transducer into your milliamp reference, the signal from the transducer, you're going to take it to your multimeter, and then from your multimeter to ground to actually measure the milliamps coming off the transducer. Yeah, so this is what I recommend. You can use just one 9-volt battery. The dude that you shared, I looked at his wiring diagram. In fact, I took a picture of it. I have it. I've got too much stuff. This is actually a picture of his wiring diagram. And it's actually very simple. What he's doing is he's bringing, he's got the two 9-volt batteries with 18 volts. He's got a switch, right, for here to turn it on. I think that chip is what the one I posted uses. He did one box with one 9-volt battery and one with 2. Okay. Possibly he was using a bit of a breakout board, which is a bit unnecessary, but, well, I don't know. It's easier, however you want to use it. Yes. So what he's got is he's got the power, and then he's got a switch, right? So the switch closes power to the regulator, and it turns on an LED to let you know that it's on, right? And then from the regulator, so the regulator has, you go in with one side and the other side is ground. So you would take to positive battery in one side and then the other side to the negative battery. And then your output over here, your output goes to your 5-volt reference. So your transducer needs 5-volt power, and then it also has a ground, and then signal out, right? So you're going to take the 5-volt power from this chip and take it to the 5-volt power of the transducer. Then you're going to take, you're going to tie the ground of the battery, so battery negative. You're going to tie those grounds together back to battery negative. And then your signal has to read back to your multimeter and then back to battery negative. Yeah, so it's actually pretty straightforward. Not sure what else. Yeah, it's that simple. I'd be happy to go over with you further in a different thing. In fact, I mean, maybe we can make it Maybe we can make that a live stream if you want. Just building a battery-powered 5-volt reference. The connectors he used, I'm not a fan of the connectors that he used in his box. I think there are better connectors than the old audio jack connectors. But, hey, it works. If it works, it works. I tend to be a fan of Molex connectors myself. But that's just me. In fact, I have a couple boxes, a couple bins here of various Molex connectors that I like to use. But honestly, it doesn't matter that much. You're using microamps. All right, back on to case. So again, yeah, if you want, we can build that out on a live stream. It's really not that complicated. What am I doing? I want my wiring diagram. Here we go. Okay, now what I am doing now is the final part of this wiring diagram. So I need to come in positive here. Right, so I'm going to take a resistor from here and bring it up to positive. Yes. And so I'm going to take that resistor to there, and then once that's there, then I need to take this pin and slink it over to the output. That might be a little bit trickier, but we'll see how it works. All right, so let me just double check that this resistor is right. It should be 200 ohm resistor. Set my multimeter. Need better leads. I'm really upset that my oscilloscope leads don't. I literally just grabbed the 18 volts power supply as the negative lead because I'm a genius. Okay, this should be 200 ohms, 220 ohms, if I can grab it. Yeah, I'm a little disappointed that I can't use 218, 19. Perfect. Okay. So I'm going to go ahead and bend this one. Let's see. That goes to there. So I want to bend it pretty much at its termination points. Yep. All right. And then I'm going to take it to here and to here. Bend that way, and then this way. All right. Yes. Yes. And then this. Oh, right. This needs to jump. This needs to jump over right here. I'll probably just add a little jumper right there. Shouldn't be a problem. All right. Now, how do I want to... Let me double check that pin out for this. I'll get those parts and touch bases. I'll tell you what, Tom. I will send you the package. I'll try to send you a link. I will attempt to send you a link to the package that I ordered because I'm pretty happy with it. It's 7805, but they actually give you the capacitors that you need, and then kind of shows you a wiring diagram on the Amazons. Of course, you know everything is the Amazons. I'll try to send you a link to that. All right, so we are backwards from that. All right, this is going to look stupid. I know I'm holding my phone upside down. I'm just kind of visualizing how this is going. So I'm going positive to ground. Right, so this is ground. And in my diagram, that's exactly... Oh, for Pete's sakes. In my diagram, that's exactly how this is drawn. I'm going positive and taking it to ground. Okay. So, what I want to do is I kind of want a little bit of insulation on this so that I'm not up against the other pins. So I'm manipulating this here pin that I cut off because I can. Alright, I'm going to take this and I'm going to bring it up here. I wonder if I can trim that one pin down because I don't need it. I probably shouldn't though. Yeah, that worked. So I can take this to here. And then I want to bend this up to here. Did I do it tight enough? I'm going to bend this one down a little bit. Parts and touch base. Man, I actually love that there's actually conversation on the chat this time around. Love it. Oh, I place way too much of my own value on the feedback of others. All right. And I can trim this insulation back. This is 100% the right way to do this. Come on. There we go. Oh man, if anybody else has any jokes or stories or questions, feel free to drop them in the comments while we are working on this. Starting to sound a little weird. Well, it's fitting because I am weird. Okay. Take this. Well, I guess I can do that. And I'm actually going to trim this up because it's going to be hard to trim afterwards. I think I need new cutters. My cutters just ain't cutting it. Ooh, bad jokes. Bad jokes galore. Alright, this is going to be a little bit tough. Oh, look at that. Okay. Alright, I think that's it. So, we got power, goes to the resistor, goes to the positive side of the diode, then goes to the negative side of the diode, back to control, which follows the wiring diagram. And that should give us what we need. Yeah, look at that. Look how fast this thing heats up. Just hit it, turn it up 320, 100, and it's in Celsius. Now that's a dad joke. Oh man, 240. I swear this thing is awesome. I actually kind of want to put together a mobile setup with this soldering iron because I genuinely believe this soldering iron will outdo the gas-powered soldering iron. The Snap-on, I actually have it right here. The only thing I use the Snap-on for anymore is heat, like hot air. Really? Oh, you're such a turd. Whatever. I'm definitely gonna have to get that fixed. So yeah, the only thing I use the Snap-on for anymore is hot air. I genuinely think this has the potential to knock out the gas-powered soldering irons as a field soldering iron. Considering how easy it is to power with batteries at, a high rate of performance. All right, got that. All right. And drop us a little doodad of solder there. All right, and then the last connection, which is kind of a wee little bit less than desirable, but it's there. Ta-da! All right, oh, almost forgot. Gotta power this thing. All right, so what I'm gonna do is I'm gonna take and lay down one of these here pieces. Ooh, if I can stop with the shakes. All right. Now let's see if I can. And then there we go. Beautiful. Beautiful. I literally just stabbed myself with a hot soldering iron. Oh, that was brilliant. Yes. right in the crease of the finger. Oh my word. All right. What did I do with my? There it is. Okay. I must be getting tired or something. All right. Trim off the excess because it looks like poo. I guess that just got over a little bit. That's all right. I think one of the reasons I actually like these flush cut pliers is these are Radio Shack flush cut pliers. And I'm a sucker for Radio Shack stuff because, just am, I guess. All right, trim up this here piece because it looks like poo. Now, let's go over this. Really? Oh, I need to fix this. Something fierce. God damn it. All right. So, we come in with 110 volts. That drops down to... Like, how is this fucking bad? So we come in with 110 volts. That splits. We biased our transformer to neutral. So every transformer has a certain bias towards the neutral, on single phase at least. So the transformer has a certain bias towards the neutral. You can measure that by measuring the output to neutral. There will be a weaker output because there is directionality involved. So that weaker output is going to be biased towards the neutral. Honestly, it doesn't make that big a difference, but hey, do it right the first time anyway. So what we did is we created our 8-volt AC side here, and it looks a little wonky because there's two 8-volt coils. This transformer in particular is like, hey, you can either do 8 or 16 volts. If you parallel it, it's 8 volts, more amps. If you series it, it's 16 volts, less amps. So we did 8 volts, more amps. We take that to the rectifier circuit over here. So I'll go to the top. So we have our rectifier circuit. So on the back of the rectifier circuit, we now have a positive 11 volts on this side and ground on this side, which is a floating ground, but I'm still going to call it a ground. You could call it negative, but I'm just going to call it ground. Put this away. All right, then we have our capacitor. Let me pull up the diagram so we can at least see that. I recently bought a 953D soldering station at auction with iron. Hot air works, and it has a power supply I actually use for my transducers. I'd like something more portable, though. Well, Tom, I'll tell you what, this soldering iron is definitely portable. I mean, you can see I unplugged the bloody thing and just throw it around. It's very portable. Anyways, so now we have our DC bus after the rectifier, right? So we have our resistor right here. So we have a resistor. And actually I did a little dance on the backside, so the resistor comes forward and then back again, just to save space. So we have the resistor right here, 100 ohm resistor, then the diode right here. So this is the diode right here. And then we have the capacitor, which bridges the positive to ground side. So we have our capacitor. And then the Zener diode. The Zener diode is like a pressure relief valve, sort of. The Zener diode over there. So that's right here. And that part is right here. On the back side, we have these two resistances right here, right here. So this is creating the voltage drop, which then sends that voltage drop over to the comparator positive, right? So we're going into comparator positive, and we take our DC up. So we're bridging. So here we're bridging the DC up, right? And then we're bridging the ground side, the floating ground, we're bringing that up. And we're tying to our potentiometer. So these two resistances right here represent a potentiometer. So it's a 100,000 ohm potentiometer. Again, the voltage, the current doesn't matter nearly as much as the voltage does. Now, the limitations of the simulation software that we used don't let me draw out a comparator per se. So this is actually an operational amplifier. Very similar. The comparator just has it's faster switching. The comparator is faster switching, and I believe the comparator has a better power to ground trace. I could be wrong though. But one of the reasons that it's a little frustrating is it doesn't let me draw out the ground side. So you have to provide a ground for the comparator and a positive for the comparator. So that's what we're doing here. Is we got our ground side coming in here, and we got our positive side coming in here, right? So this is the plus, this is the minus, this is the ground, this is the power, and then this is our signal. Our signal. So then we got this resistance right here. So we take our DC bus, right here, over, and then we have a resistance down to, yep, right here. We have a resistance, 220 ohms, down to the opto-isolator, which is this point. So that goes to the positive side, and then back because our switch is grounding. There it is. Now the only thing I have to do is set the output. Where do I want to plug the output? If I'm making this a module, I kind of want to put the output here. So the output of this opto-isolator is we use the 5 volts from the controller. So when we use the 5 volts from the controller, the entire point of this opto-isolator is to separate the voltage. So we have line side on one side and control side on the other. So the computer exists completely separate from the line voltage. That way there's no chance of it, blowing anything up. So the opto-isolator, yes, so we're coming in positive, going out negative on there, so that's correct. I'm going to need to add a 220 ohm resistor. I think that's it right here. The 220 ohm resistor goes to the 1 point, and I didn't actually draw it. Yeah, that's grounding that out, which turns that on. So every time this voltage goes above, that grounds, that turns on. Right. So then I take my voltage, it'll be high unless I do on the backside. And if it's on the backside, it'll be ground. Backside, then resistor, it'll be ground until it closes. So, all right, I have to do a little bit of thinking here. I wonder if I should draw this out. Should I draw this out? I don't rightly know. How long have we been on? Oh, Jesus Christ, it's almost 2 hours. Okay, so I should draw this out, but let me see here. All right, this needs to go in there. All right, let me do some thinking here. All right, so when this voltage goes higher, this will ground out, it will turn that on. So anytime this voltage goes higher than this voltage, it will ground this and turn on. So that means it'll be on for that period. So when it goes below, so when this goes negative, this will... Shit. I'm going to have to draw this thing out. Let's go to the computer. Alright. This chair is a giant pile of garbage. Alright, what I'm going to do is... I know, the camera's odd. So... I'm going to go to screen capture. Let's bring on our OBS. Right? Okay. Start virtual cam. And let's see. OBS cam. That's that one. Elgato bench cam, OBS cam, collab cam. Alright, I'm going to make a new source. Video capture device, add source, webcam, good enough. Add source. I need to size it. Transform, fit to screen. Yep, alright. Now, I want to bring out my circuit FJ. I'm going to reduce this. Circuit FJ, file, open file, and zero cross. Is this the one I want? Yep, that's the one I want. Shawing! Sweet. Okay, now, what I want to do is I want to add a voltage input, one source, right here, 5 volts, that's good. Now I want to draw a resistor, right here, 1K, oh, I missed. Right there, and then I want to, alright, so I'm going to delete this ground. It's going to mess up all the readings. I don't care. Now, maybe I should leave it there. Alright, and then I'll just put a ground right here. Now, alright, so that indicates that. And I don't need this one, so remove this scope. I don't need this one, remove this scope. What is this? That doesn't really matter. Alright. Do-do-do-do-do. Now I want to scope this. Right. So with our voltage low, our trigger's low, which means we're high. So if I change this, let's do ground, and I add the resistor to here instead, that's always going to be up. Bring it off of here and view in new scope. There we go. All right, so I want the resistor on the back side and read that. That's what I'm looking for. Now, if I change edit to 50,000 and edit to 50,000, that should change. Yep, there we go. That is doing exactly what I want it to. So, if you can imagine, oh, dear Lord. Oh, that still works. So, if you can imagine what we have here on the bottom left oscilloscope reading, we have our red line is our negative, and our green line, which is the bumpy line, is our reference, right? And I can point out which one's which on there. The higher that goes, the bigger space we get on, so the right oscilloscope reading, if you go to the top side, so like right here, this is 0 volts. If you look on the left one, that is, well, 41 millivolts, but that's 0, right? So we're in the middle of this pulse. But what this allows me to do is I set the computer to trigger a timer on the rise of right here. So right there, it would trigger a timer, and at 0 seconds, this allows us to lead the controller so that, umpteen milliseconds. It looks like right now we have about 1 millisecond of time to lead the controller so that we actually bang it right on 0. But that's what we're trying to do. All right, so I want, sorry, let me go back to, I'm going to turn this off. We're going to go back to the bench. So I want to take positive and put the resistor on the ground side with the, so yeah, put the resistor on the ground side with signal. Okay, so positive goes to the switch, signal comes from the switch, and then resistor to ground. Ta-da! Now, I'm going to do the 3 pins here, and I kind of want to do the 3 pins right over here. Looks like we lost some viewers. So I kind of want to do the 3 pins. Why is that not fitting? There we go. So I kind of want to do the 3 pins right over there. Alright, I need to pull up the pin out for the opto-isolator. Yeah, optocoupler. Alright. So that's how it's sitting. So we want to come in here and then come to here. Alright, so this one needs to come over and tap to that, and then this one comes over. Right, so resistor to ground. So it would actually be beneficial, but then it's not on the same plane. Kind of want it to be on the same plane. Fuck it, it'll work. Alright, I'm going to go ahead and solder this. I'm going to go ahead and throw a little bit of solder on that bus to hold it in place. And then I'm going to need to denote the marking somehow. So I want my 5 volts. My 5 volts goes, while that's heating up, I want my 5 volts go straight to there. And then, yeah, so 5 volts goes straight to there. And then that goes straight to here, and then jump. Oh, done. Figured it out. Good. Do I have a bridge that fits that? I do. Look at that. Gotta love it. Got to love it. Well, it mostly fits that. Another one. All right. So if I go on the back side, and then tie this over to there, like that. Okay. Now, yes, because that's going to be signal. And then I want to tie, yep, I need a 1K ohm resistor. Okay, this is warm now, so I can heat that up. Get a little tip tin on there. Good night. You are not being helpful. Get in there. Ouch. Imagine that. Stuff gets hot. that in? Yeah, it's a little crooked. There we go. All right. Well, that's actually in there. I'll go ahead and solder this one in. Yes. Solder this pin to here. All right. Do a little better job of soldering these together. There we go. Gotta solder these together. There we go. All right, now I just need a 1K ohm resistor. Okay, so that's 5 volts. Signal back. Now I need to jump from here to the resistor, 1K ohm. Oh, this is going to be possibly a little difficult. So, does anybody have any comments or questions or stories or anything like that? Now's the time. Well, I'm trying to find a 1K ohm resistor. I know I have them. Just gotta find them. Should probably do it. That's 5K. Is it 5K? 200. 22,000. 100. 5K. 22. 10K. Oh, that's 10. 510. 3K. 200. 5K. 100K. 300. 150. Now, realistically, I should be able to. Yeah, I should add a jumper so that. Nah, do I need to? Maybe I should for testing purposes. I think I can add a jumper so that I can take power off the 5-volt rail to feed that opto isolator, so that when I'm testing with an oscilloscope, I can just jump that out and have the built-in power for that 5-volt reference. Yeah, I think that'd be a good idea. I think I'm going to do that. Shouldn't be too hard. And I can just use circuit board jumpers. 47, 680. It's always the last one you check. You ever notice that? Anytime you're looking for something, still not 100% clear on what you were doing, but your explanation was good, and I'm starting to get it. If my explanation was good, you'd be 100% clear on what I was doing. So, how do I say this? To really, while I'm looking for this resistor, try and bring this home down, let me think of a different way to explain it. If you think about, oh, I need a whiteboard for this. I don't have it, it's all the way over there, but that would be handy as hell. If you think about the power that comes out of your wall, right? So wall outlet power. It is what's called a sinusoidal pattern, right? It does this number, you know, going up and down. Looks real wavy kind of thing. What that is to understand what a sinusoidal pattern is, it's the voltage. You got to understand when the generator's, spinning and the magnetic field is crossing the wire to generate the voltage. There's a process. It goes, from this point at its strongest and then weak again. So, and it's doing that repeatedly. So the magnetic field is going weak, strong, weak, and then back again, right? And that's why you get that sinusoidal pattern. That sinusoidal pattern is a linear representation of the spinning of the magnetic field in the generator. So, yeah, we'll just stick with that. The thing is, in AC current, alternating current, right? Alternating current is DC, direct current, that switches. It alternates. So what's happening is you're going from 0 up to 110. Well, it's actually like 171.6, but 0 up to 100, and we're going to say 110 for nutshell. So you're going 0 up to 110, back to 0, down to 110, because guess what? Our magnetic field has spun, and now we're on the backside of the magnet, right? So we're going positive 110, back to 0, down negative 110, back to 0, up to 110, back to 0, down to negative 110, back to 0. That's what AC is. It's doing positive to 0, negative to 0, positive to 0, negative to 0. If I want to control something that uses AC and I don't want to go through the whole shebang of a VFD, like if it's just something really basic, like a simple fan, or even better, a resistive heater, then I don't want to go the whole route of VFD. VFD is a whole bunch of other stuff. What I can do is I can take a computer and tell it, when I see 0, right? Say I only want to spin at 50% speed. What I can do is there's on AC, on the AC that comes out of your house, it's doing this, positive to 0, back, negative to 0, positive to 0. That space between that positive 0 to 0 is about 8.25 milliseconds. If I tell a computer, start counting at the 0, right? And count 4.15 whatever milliseconds. All right, it's going to go, all right, here's 0, 1 millisecond, 2 millisecond, 3 millisecond, 4 millisecond, turn on at 4 milliseconds. So we're going to turn on at 4 milliseconds. So now, instead of the whole pulse, we're getting half the pulse, right? That's called phase angle switching. So the name is a little bit harder to understand, but that's what we're doing. We're telling the computer to wait a period of time and then turn on. And then at the next 0, it does it again. So we, wait 4 seconds, 4 milliseconds, turn on. We catch half that pulse. And then we wait, because here's a 0. Okay, wait 4 milliseconds, turn on. We get the other half of the pulse. Wait 4 milliseconds, turn on, get the other half of the pulse. So that's how you do phase angle control. It's turning what comes out of your wall into a PWM, essentially. But in order for that to work, we have to know where 0 is. We have to get that timing right. If we don't always start at 0, then you can end up with feedbacks that just kind of throw everything out of whack, and you end up with harmonics that's a whole nother story. You just don't want that. So you want the computer to know where 0 is. That is what we're building right now. We're building a circuit that allows us to tell the computer where 0 is. But because everything takes time to switch, we can tell the computer that 0 happened 2 milliseconds before it actually happened, so that by the time the computer thinks about it and does its thing, it switches on right at 0. So that's what we're doing. We're detecting the 0. We're telling the computer where 0 is, but we're fooling it into turning on like 2 milliseconds ahead of time to make up for the delay in all the turn-ons. That's what we're doing. So it's all about getting that 0 point on that IAC sine wave so that the computer can count from there. Hopefully that was a better explanation. I don't know. I'll keep trying until it becomes clear. Ah, found it. Ta-da! 1K. Took you long enough. Yes, it did. Now I got to put all this back. I definitely need to come up with a way to store resistors better. Because this is for the birds. But even this is better than what I had last time. What I had before. What I had before was literally just a pile of... So the soldering iron automatically turns off. Period of time. So now it's got to heat back up again. Do a little cleaning of the tip action here. Oh, it's got to heat back up. I'll take a drink. Got it. Yay! You got it! I love teaching. That has always been fun for me, the teaching. Tom, I don't know if you remember back in the UTI days, I actually used to, when I ran the tutoring department, I actually, I'm helping create a tutoring department in the place where I work now. So we've had a couple guys having a hard time passing the entrance exam to the union, so I'm making a tutoring department for that. All right, now I am going to do this on the backside because I think it's easier, and I'm just going to be a bum about it. The resistor there. Because I can be. Because I can be. Because I can be. Ooh, would that be cheating? I think that would be cheating. I'm going to try and stick this down the same hole that came out of. That would be something else. Is it going to work? Is it going to work? Is it going to work? Maybe? Oh, it didn't work. That's okay. That's okay. Doesn't matter. All right. What I want is a winning lottery ticket. All right, now I know I'm getting tired. I'm starting to sing. That's what he said. In my job, I sometimes get the chance to help our young techs when they're stuck. It's very rewarding. I agree. It is very rewarding. I've also found that if you are having a hard time understanding something, oddly enough, it actually helps to teach somebody that something. I can't really explain it, but it does. That did not go the way I wanted it to. There we go. Now you're in. Come on. There we go. Ta-da! All right. Oh yeah, I wanted to add a pin to bridge the voltage over. All right, let me clean this up. And I think this is probably should get a new flush cut cutters. But I like my Radio Shack pieces, because I'm just kind of nostalgic that way. I'll tell you what, absolutely nobody is going to watch the video of this. We're probably over 2 hours by now, aren't we? Yeah, 2 hours and 10 minutes. Oh my lord. All right, one more piece. One more piece. I want a pin to be able to take voltage from our DC 5-volt bus and send it to... Oh, I guess I would need to go back to ground then, too. That shouldn't be a problem. So I need DC 5-volt, which is right here. Alright. Stay. That is not going to stay. Oh boy, how am I going to... This one's going to be a doozy. I heard that, Rupa. Alright, turn that back on. And I'll need a ground too. Yeah, because I got to take it back to ground. Alright, so the circuit's pretty much done. What I'm doing now is I'm adding some points so that for testing purposes, to confirm that the circuit actually still works, I can bridge some voltages over that you would not normally bridge. Is that worth a shit? Is that joint worth a shit? I don't know. It really doesn't look that good. That's better. Yeah, good enough. Alright, and the negative side. Oh, that'll work. Right there. That will give us our negative. Go in. Okay. Oh, for... These are not convenient. Alright, I'm going to have to load up the soldering iron. Right. Hook this in. And it's not working. It's not working at all. There we go. Just needed to add some flux. There. All right, I think that's it. Oh God, that didn't. Oh Jesus, that did not. That did not go right. Not even a little bit. Do I want to know what time it is right now? 10:17. That's not too bad. That solder joint is cold as hell. So this will let me take negative over. There we go. Mucho better. Yeah, that's mucho better. All right. So that will let me take 5 volts and ground from this circuit, feed it back through here. Then I'll be able to read on the oscilloscope from its own power. Yes. Yep, that'll work. Should be fine. All right. Looks like I need to put the, all I need to do is install the comparator in and give it some voltage. Okay, let me just double check here. I've got my 5 volts. Yep. So I got my 5 volts to here, right? Yep, 5 volts. 5 volts comes into here. So I got my... Oh no. Oh no, I think I did it backwards. Shit. Alright. I'll be right back in a minute. Alright. Now I'm worried that I messed up. Shoot. I did. 100% I did. I did. I totally got this wrong. So I have VCC coming into there. It actually needs to come into here, and ground needs to come into here. And output to here. Did I get that right? Yes. How did I... No, I got it all wrong. Mother Hubbard. Yeah, this all needs to change. Every bit of it. Yeah, this needs to move to here. This needs to move to here. This needs to move to here. Or I move this whole thing up. if I move the whole socket up, then that aligns because, so I have my positive coming in at the bottom, right? So if I move the whole thing up one, that will take this pin up to positive, this pin up to negative, like it's supposed to be, and then reference, and then VCC will just pin right here. And on this side, on this side I need to unbridge this, because that's going to be there. And I need to take ground up to here, right? Because ground is right there. Okay. Well, I guess we're not testing it tonight. Because I messed this up. I guess I'm going to have to go through and, where's my fuck up fixers? Where's my fuck up fixer strip? I have some fuck up fixer strip. Well, I have my desoldering iron here. That's fantastic. But I also have some fuck up fixer strip somewhere in here. Solder wick. Yep. I'm going to have to get the solder wick out and desolder these connections. Move this up one. Tie this ground over. Yeah, that can stay where it is. I'll just continue this ground over. In fact, I may actually just pull that whole thing up too. Shoot. Yeah, I goofed it up. Yes, indeed I did. Well, shit happens. Everything else should be alright. Alright. I think this is where I'm going to cut it out. We're going to cut out the live stream. I'm going to go ahead and start fixing this so on the next live stream we can actually test it. So that's what I'm going to do. I'm going to go ahead and start fixing this mess up. And yeah, I'm going to fix this mess up. I'm kind of thinking I might wait to do the next live stream. I am building a better power box. You probably noticed on the last live stream I did some really shady crap to get my 110 voltage over here. I want to do a much better job of that. So I might wait until all that stuff arrives so I can put that together. Because I want to add a switch and an actual fuse, like a circuit breaker, to feed this. Yeah. You know what? Nope, that wouldn't work. I was going to say I have a power supply, but that feeds DC and I need AC, so. Yeah, so I might wait to test this thing until I make an actual, like, decently protected power supply box for this. Yeah. Where I went wrong as I'm fixing it. Yeah. Yeah. Or we just don't go wrong in the first place. I don't know. Whatever. All right, guys. Thank you very much for watching, everybody. I appreciate you stopping on by. This stream is excessively long. I get that, but I very much appreciate, especially you, Tom, for coming in and watching. Let me know when you get the stuff in. I'm going to try and send you the link to the voltage regulators that I got from Amazon, because it comes with the capacitors that are recommended for that regulator, so it's just better that way. And they're not expensive. I think it's like $10. It's really not a thing, and you get like 20 of them or something. I don't know. I'm going to fix this off camera so that when we come back for the next live stream, yep, that's what we'll do. On the next live stream, we're going to put together the 110 volt power supply breaker box. We're going to put together a 110 volt breaker box to be able to feed 110 volts to this that are protected, so we don't short anything out and make it go poof, hopefully. And yeah, hopefully then in the next stream we'll put that together and we'll test this baby out. So thank you very much for coming, everybody. I really appreciate it. And I guess I'll see you on the next one. The parts. When is the next live stream? That is a good question. I am glad somebody asked that question. When is the next live stream? Oh, man. I'm thinking, so the parts are on order for that box arriving tomorrow, arriving Saturday. So the circuit breaker arrives on Saturday, possibly Sunday. So I'm thinking Saturday, Sunday for the next live stream. Yeah. I will obviously do the same thing on the Facebooks. On the post, there will be a post when I for sure do the when we plan the live stream, and we'll get to doing it then. Hopefully we see this stuff actually work. Thank you very much, everybody. Have a good night. I'll see you next time.